Yes, sir.
So, good afternoon to all of you. As we were seeing last lecture, that Goodman diagram, and it's related to what the fluctuating stress. All background of this fluctuating stress, and when we are going to design against this fluctuating type of stress, which is the product of fluctuating type of load, then this Goodman has just given us a simplified tool in our hand that by means of referring that graph, one can easily find out various values which are required for the designing of any component against the fluctuating type of stress. Whereas he has considered that Moore's experiment by means of which we have calculated the endurance limit stress, and that endurance limit stress he has taken as a one criteria, and as well as the normal that SUT, that is the ultimate tensile stress, is he has selected as other criteria. And by using these two stress, he has just given that diagram, and he has graphically represented that values related to the failure. Also, he has given the region by means of which we can get the safe or safety related to the design. And of course, we are going to use the factor of safety by using Goodman's diagram. But after long period of that diagram which has used, and nowadays also we are referring that diagram, Goodman's diagram. One more engineer, he thought that if it is possible, because that Goodman diagram, as yesterday you asked question that whether the point, if that point is lying on the line, then what will happen? In that case, the failure may occur within the specified time only. It will not go for the infinite life. So in such cases were happening, and this Goodman diagram was not only sufficient, this Goodman diagram, to give a clear picture about the fluctuating type of stress. So what exactly he has done, he has taken this SUT, that is the ultimate tensile strength he has considered. Whereas this ultimate tensile strength is applicable for the brittle material as well as it is a property of ductile material also. But in his diagram, he has not mentioned anywhere the property of ductile material, that is the yield strength, where the yielding gets started. So Soderbergh is the name of that engineer who has again given some important applications of his diagram. So what he has considered that ultimate tensile strength and yield strength also. So when we are going to plot yield strength on the graph, same graph where we have plotted this ultimate tensile strength, then definitely this yield stress will be less than the ultimate tensile stress. Whereas the ultimate tensile stress can be implemented for the both type of material, that is brittle as well as for the ductile. But the ultimate tensile stress is the property of brittle material. More or we are going to consider it for the brittle material. And for the ductile materials, we are going to say that ultimate that where the yielding gets start, that point or that stress we are going to concentrate more, and which is definitely less than the ultimate tensile stress. So what Soderbergh has done, if you see this diagram, what the Soderbergh, he has taken the same reference of Goodman diagram, and he has plotted this endurance stress on y-axis, whereas the mean stress on x-axis. Now he has varied that mean stress value up to the uh, yield strength only. Now here only if I want to modify it, or if I want to show the Goodman diagram, then what change I have to make, that this from sigma E, or normally we call it as a SE also. If I draw one line, which will be up to the this black line, which will be basically up to the x-axis on which we have mentioned the mean stress, and up to that, what will happen? Okay, the point which I have to mention here will be sigma or S ut. Am I right? So when we are going to mention this point, now this line, black line, will become the line which is stated by the Goodman. Whereas Soderbergh has made slightly change in that, and he has considered this ultimate tensile strength, and the region by means of which it has get varied. This is the region where, as our yesterday's question, failure was more. The failure which was occurring in that triangular area, which has get reduced in the Soderbergh diagram, because here you can say this is the Soderbergh line, okay, and this is Goodman line. Now this, if we are going to say this Soderbergh, it is coming under this Goodman's triangle, right? This triangle AO, which we have mentioned here as a B point in previous case. Now B point has get shifted here, but previous case we will say it as a X point. Okay, so when we are going to consider this triangle, which is up to the X, here I will mention this point as X point. So when we are going to consider this triangle AOX, then this AOB triangle is coming under or is the part of this triangle AOX, but it has get reduced. This area has get reduced, and this area where the maximum failure was occurring. So people definitely like what the Soderbergh has done, because in that case the failure was less. If we are going to follow the Soderbergh line, then definitely the unsafe area has get reduced and we are moving towards the safe area. So that diagram becomes more popular than the Goodman's diagram. But no doubt that Goodman has given some, or he has done some initiation regarding reducing effort of designers. Every time it is not necessary to go for the more test. Every time it is not necessary to calculate the notch sensitivity, all factors, and uh, every time it is not necessary to do the experiment which the Moore has done on the standard specimen. Only by referring that diagram, one can easily get the idea of safe region. Okay, these are only for our guidance. We cannot say that this Goodman or Soderbergh line exactly will be implemented for the particular case. No, they are giving us some guidelines, and based on that guidelines, designer has to decide that where we have to keep our stress, in which region we have to keep the stress, induce the stress in any component while we are designing, and that designer will decide. So this is going to become one guideline for the designer, and Soderbergh has also given that guideline by means of reducing the area of that triangle, and that is known as a Soderbergh line. Okay, here it has written now this Soderbergh line. Okay, now based on this Soderbergh line, again we can go for the calculation, same way as we have done in case of Goodman diagram. Okay, and based on which we can calculate the factor of safety which we have to select while we are going to design any component against the fluctuating type of stress. So that is the main utilization of these diagrams, or that is our main motto to study all these diagrams. Okay. So when we are going to consider the Soderbergh line, I'll delete it. Now when we are going to consider this Soderbergh line, at that time, this Soderbergh line is applicable more in case of ductile materials. One can make that conclusion. And that Goodman okay, that is again vague statement. Okay, these are the only guideline or These are the only guiding statements. You cannot again affirm on that. But if you are going to select the stress which is below that line, then definitely it is coming under the category of infinite life and safe region. Are you getting me? So let us consider this point P, okay, and we will analyze that relationship between the various parameters. Like first parameter which we have mentioned on x-axis is the mean stress, okay. Then the second parameter which we have mentioned on y-axis, that is the yield stress, okay, or variable stress. Now these two values, from these two values, if you are going to join a line passing through point P to the, or it is extended to the x-axis as well as to the y-axis, and where it is going to touch the y-axis, that will call as a limited value, or what we can say, limiting value of our point of interest P of stress. And how we can calculate it? It can be calculated by means of endurance limit divided by factor of safety. Whereas same way we can find the value of the yield stress. Now here not ultimate stress, it is a yield stress. Okay. So yield stress divided by factor of safety. Or when we are going to get this value is equal to yield stress divided by factor of safety. If you are knowing the value at point D, then you can calculate factor of safety, right? Vice versa, you can do the calculation. So we can calculate this value. And based on this similar triangles, again, as we have done the calculation in case of Goodman diagram, same type of calculations we can do for the Soderberg diagram also. Now, when I'm moving to the next slide, before moving to the next slide, let me know, do you have any question? Hello, regarding Soderberg and Goodman, because I have compared that two diagrams also, Soderberg diagram and Goodman diagram. Now diagram, it doesn't mean, it is a graph actually. And while we are going to draw it, that's why it is called a diagram. Basically, it is a graph. So have you understood what the Soderberg and Goodman lines are and what they are indicating? What is the significance of that Soderberg line and Goodman line? Okay. If you have any question, you are free to ask. Otherwise, we'll move to the next slide. Hello?
No doubt, sir.
No doubt. Okay. It's good. Anybody else? And Nilesh Kadam has joined recently. Nilesh, do you have any doubt related to the this slide?
No, sir.
No. Okay. Anybody else? Now let me ask one question, that is it necessary to go for this Soderberg line, or is it really required to have this Soderberg diagram, and we have to consider the Soderberg diagram, or it is just a wastage of time? Saurabh Wadekar,
Hi, sir.
can you explain what just now I make the comment that is it a wastage of time or it is going to give some significance, the Soderberg line? Should I repeat my question?
Uh,
Hello?
Hello.
Do you get my question?
No, sir. I don't.
Okay. So, is it really required to have that Soderberg diagram to be studied, or only sufficient? It is sufficient to have Woodman, and it is just wastage of time. Whatever.
Yes, sir.
So, What is your opinion? Hmm? तुम्हाला प्रश्न समजला का वाडेकर?
नाही सर, समजलं नाही.
प्रश्न समजला. माझा प्रश्न हा आहे की सोडरबर्ग डायग्राम किंवा सोडरबर्ग लाईन जी आता आपण एक्सप्लेन केली, बघितली, ती खरोखरच अभ्यास करायची गरज आहे का? फक्त गुडमन डायग्राम वरनं किंवा गुडमन लाईन वरनं आपल्याला त्याची सगळी आयडिया येते आणि सोडरबर्ग डायग्रामची काही गरज नाही. वन शुड नॉट गो फॉर इट. तुम्ही त्याचा अभ्यास करायची तशी काही गरज नाही.
एखादा पॉईंट जर सर ए बी लाईनवरच असेल तर त्याची गरज आहे ना त्या डायग्रामची.
ओके, एबी लाईन वर म्हणजे कुठल्या संदर्भात म्हणता? म्हणजे गुडमनच्या डायग्राम वरची एबी लाईन का सोडरबर्गच्या डायग्राम वरची एबी लाईन? आता जी समोर स्लाइड वर दिसते ती सोडरबर्गची लाईन दिसते. ओके, मी गुडमनची पण तिथे काढून ठेवतो.
समोरच्या ह्याच्यावरची सर.
हा, गुडमन, आता
Diagram.
गुडमनची लाईन आहे, एक्स लाईन आहे. हा, आता काय म्हणताय तुम्ही? हा,
अजून
हॅलो.
एकदा सांगा सर.
हा, आता सांगा तुम्ही काय म्हणताय ते. तुम्ही म्हणताय ती गरज आहे, बरोबर आहे. कुठल्या एबी लाईन वरच्या पॉईंटला गरज आहे का एक्सच्या लाईन वरच्या पॉईंटला गरज आहे?
ए बी लाईनवर.
एबी लाईन वर. हा, एबी लाईन वर पॉईंट आला तर गुडमन म्हणतोय की तो सेफ रिजन मध्ये आहे. तुम्ही काय बाकीचा काय विचार करताय? हा, what is your opinion? I'm saying that yes, Soderbergh has given his statement, Goodman has given his statement. No doubt that as we are studying all these things, it means that it carries some importance. What is your opinion?
रिक्वायर्ड आहे सर ते.
रिक्वायर्ड आहे कशासाठी? कशासाठी? डक्टाईल मटेरियलसाठी ते रिक्वायर्ड आहे. कारण प्रत्येक वेळेला आपण जे मटेरियल घेऊ त्याची स्ट्रेंथ अल्टिमेट टेन्साईल स्ट्रेंथ असेलच असं नाही. आपल्या बऱ्याचशाच कंपोनंट जे आपण डिझाईन करतो त्याच्यामध्ये डक्टाईल मटेरियल बऱ्याचदा वापरतो आणि ते जे डक्टाईल मटेरियल आहे त्या डक्टाईल मटेरियलला अल्टिमेट टेन्साईल स्ट्रेसचा उपयोग नाही. त्यासाठी पाहिजे यील्ड टेन्साईल स्ट्रेस, एस वाय. ही अगेन स्ट्रेंथसाठी वापरलं जातं. ओके, तर त्या केसमध्ये फेल्युअर आपल्याला समजायसाठी इफ वी आर वेटिंग अप टू द अल्टिमेट स्ट्रेस, then failure has started from the yield, but we are waiting up to ultimate stress. Okay, so that is going to give us wrong prediction of stress. Okay, or the failure occurs before that ultimate stress. It has occurred at yield stress only. That's why this diagram is important. Okay, and if you are going to compare these two lines AX and AB, okay, then AB is not beyond the AX. It means that it is coming under the safe line only, and we are making our design or product more safer. Okay, but if you cross this AB line for the ductile material, then we cannot assure that it may not get fail for the finite cycles or for the infinite cycles. We are not sure. So to have the surety in our design, to increase our confidence level, a design response confidence level, this Soderbergh line has given more, what we can say, safe and predictable results. Okay. So once again, just I will take the overview. दिस AX लाईन जी गुडमॅननं सांगितलेली होती त्यांना SUT पर्यंत, कारण बऱ्याचदा काय होतं की ज्यावेळेला फेल्युअरचं तुम्ही चित्र बघता कुठल्याही फ्लक्च्युएटिंग स्ट्रेसच्या अंडरचं फेल्युअर, ते फेल्युअर जवळजवळ ब्रिटल मटेरियल सारखंच फेल्युअर आहे, म्हणजे एकदम मोडलं जातं किंवा तुटली जाते ती वस्तू जर रिपिटेटिव्ह स्ट्रेस आपण वापरत गेलो तर. ती काय अगोदर इंटिमेशन देत नाही, म्हणजे जसं की आपण नकल जॉईंटला बघितलं. नकल जॉईंट जर तुटायचं असेल तर काय होतं की अगोदर त्या जॉईंट मध्ये असलेल्या सगळे कंपोनंटची लांबी वाढेल, ताणला जाईल तो. ओके. त्याच्यावर अजून आपण स्ट्रेस अप्लाय करत गेलो तर मग तो तुटेल. ओके. तसं फ्लक्च्युएटिंग टाईप असेल तर तो ताणला जात नाही किंवा त्याचे डायमेन्शन्स वाढले जात नाहीत. फ्लक्च्युएटिंग टाईप स्ट्रेस मध्ये काय होतं की सडनली कळतं की तुटला आहे तो. त्यामुळे गुडमननं काय केलं होतं की इन्स्टेड ऑफ कन्सिडरिंग यील्ड ही हॅज कन्सिडर्ड अल्टिमेट टेन्साइल स्ट्रेस, कारण सगळे तिथं मग डक्टाइल मटेरियल तिथे ब्रिटलच आहे, लगेच म्हणजे कुठलंही इंटिमेशन न देता तुटले जातं. असं आपण त्या अगोदरच्या फेल्युअर क्रायटेरियामध्ये किंवा जे फेल्युअर्स ऑफर होतात, फटिक फेल्युअर ज्याला म्हणतो आपण, त्याच्यामध्ये बघितलंय. त्याच्यामुळे गुडमननं त्याच्यावर स्ट्रेस दिला होता. पण ज्यावेळेला आपण गुडमनला फॉलो करायला गेलो त्यावेळेला असं समजलं की येस, त्यानं सांगितलेल्या ट्रायंगलमध्ये म्हणजे AOX या ट्रायंगलच्या आतमध्ये जरी पॉईंट असला आणि तो जर त्यानं सांगितलेल्या लाईनच्या जवळ असेल तिथे सुद्धा फेल्युअर ऑफर व्हायला लागलं. त्याच्यामुळं सोडरबर्गनं काय केलं की ठीक आहे, त्यानं अल्टिमेट टेन्साइल स्ट्रेस घेतला होता, आपण यील्ड टेन्साइल स्ट्रेस घेऊन बघूया. ती लाईन त्याच्या पण आत आली आणि ह्या यील्ड स्ट्रेसला जर आपण शेवटचा स्ट्रेस म्हणजे फेल्युअरचा स्ट्रेस जर म्हटलं तर त्याच्या आतमधले स्ट्रेस हे सेफ लाईन मध्ये येतात किंवा सेफ डिझाईन मध्ये येतात. ते ठीक आहे, सेफ्टीच्या दृष्टीने ते चांगलं झालं. ओके. So we are studying now. Finally, we'll compare these two diagrams also. Now, this diagram, by considering this diagram, we can go further. Yes. Anybody has doubt? Okay. Now, I'm getting my voice back.
Yes.
Hello.
हॅलो सर.
Yes.
सर ते डायग्राम ओपन करा. प्रिव्हियस.
हा.
सर जर पॉईंट ते सेफ लाईनच्या पुढे क्रॉस केला आणि जर
इथं.
पॉईंट जर सोलार लाईनच्या जरी जवळ आत असला तरी पण फेल्युअर होऊ शकते की.
कुठल्या लाईनच्या आतमध्ये? आता हा पॉईंट की पॉईंट आहे.
हा, त्याच्याच पुढे जर सेफ लाईन जर क्रॉस करून पुढे गेला पण सोलार बर्फच्या जरी आत असला तरी पण स्मॉल ह्याच्यात फेल्युअर होऊ शकतं की.
एक मिनिट, मी पॉईंट घेतो, मला त्याचं लोकेशन सांगा तुम्ही. आय मूव दॅट पॉईंट. इथं पॉईंट असेल तर?
हा सर.
हा, इथं पॉईंट असेल तर फेल्युअरचे चान्सेस नाहीत ना. फेल्युअर कधी होईल की ज्या वेळेला हा स्ट्रेस आहे, आता मी इथं जो पॉईंट मी घेतलाय त्याचे स्ट्रेस लेवल करतो अगोदर. एक्स ऍक्सिस वरचा त्याचा झाला व्हेरिएबल स्ट्रेस. ओके. मीन स्ट्रेस ही जी व्हॅल्यू आली त्याची ती मीन स्ट्रेसची व्हॅल्यू आहे. वाय ऍक्सिस वरची जी व्हॅल्यू येईल आपल्याला ती व्हेरिएबल स्ट्रेसची व्हॅल्यू आली. ओके.
ओके.
आणि या दोन्ही म्हणजे याच्यातून पास होणारे रेष which will cross to x axis and which will cross to the y axis also. मला पॅरलल रेस करायचे. ओके, ठीक आहे. I will go it once again. ओके. आता ही रेज, I'll change the color.
हा
Okay. आपण change करतो. आपण change करतो. आता सांग. नाव ही जी आपल्याला व्हॅल्यू मिळणार आहे इथं, ती व्हॅल्यू कुठली असणार आहे? व्हेरिएबल मीन स्ट्रेसची. ओके, सिग्मा एम. ठीक आहे. आणि तशीच वाय ऍक्सिस वर जी व्हॅल्यू मिळेल आपल्याला, ती असणार आहे सिग्मा व्ही. ओके, आता सांग
हा
कुठे फेल्युअर, आता ह्या पॉईंटचं फेल्युअर ऑकर होणारच असं म्हणताय का?
हा म्हणजे सर सेफ लाईन जर त्यानं क्रॉस केली त्या पॉईंटनं,
कुठली कुठली सेफ लाईन आता ह्याच्यात?
सीडी
कुठली?
सीडी स्ट्रेस लाईन.
सी डी. ही सेफ स्ट्रेस लाईन आहे. ही काय केलंय आपण की एक ऑर्बिटरी कुठलाही पॉईंट घेतलाय पी. आता मी ह्याला सेफ लाईन म्हणू शकतो, की जे
ओके
ब्ल्यू कलरचे आहे त्याला सेफ लाईन म्हणतो मी. होईल काय फक्त की ही जी व्हॅल्यू मी काढली आता, ही व्हॅल्यू
हा सर.
या केसमध्ये कुठली व्हॅल्यू होईल मग? ही व्हॅल्यू होईल. ओके, ही जी व्हॅल्यू आहे दॅट व्हॅल्यू विल बिकम SE डिवाइडेड बाय फॅक्टर ऑफ सेफ्टी. बट SE हॅज कॉन्स्टंट व्हॅल्यू, राईट?
हा
आता ही व्हॅल्यू, समजा ही व्हॅल्यू आलेली आहे 210, तर ही व्हॅल्यू येईल त्यापेक्षा जास्त म्हणजे 250. आपला यील्ड स्ट्रेस जो आहे तो कॉन्स्टंट आहे, समजा तो आहे 300. 300 डिवाइड बाय द फॅक्टर ऑफ सेफ्टी हा आपल्याला पाहिजे 210, आणि हा 250 डिवाइड बाय सेम फॅक्टर ऑफ म्हणजे ते यील्ड स्ट्रेस आहे तो, इंड्युरन्स स्ट्रेस आहे तो. ही जर व्हॅल्यू काढली तर फॅक्टर ऑफ सेफ्टीची व्हॅल्यू चेंज झाली इथं, आणि हे तुमच्यावर डिपेंड आहे की फॅक्टर ऑफ सेफ्टी मला इथं 2 ठेवायचा आहे का 1.5 ठेवायचा आहे. बट हिअर फॅक्टर ऑफ सेफ्टी विल बी देअर, राईट? इफ आय एम गोइंग टू कन्सिडर this stress as a endurance stress only, what will be the factor of safety? Hello? For this black line, what will be the factor of safety? Abhijit?
हॅलो.
Huh?
हॅलो.
हा हॅलो, बोला.
हॅलो सर, आवाज आहे ना क्लिअर?
आता येतोय?
हा हा हॅलो सर.
हा, आता ही जी ब्लॅक लाईन मी ड्रॉ केली ही,
हा
ह्याचा फॅक्टर ऑफ सेफ्टी किती येईल? 1, बरोबर आहे, 1च येईल.
हा
आणि जो आपण आता पॉईंट घेतलाय तुम्ही सांगितलं तसं,
हा
या पॉईंटचा फॅक्टर ऑफ सेफ्टी
लेस
डेफिनेटली 1
होणार.
पेक्षा जास्त. हा,
फॅक्टर ऑफ सेफ्टी 1 पेक्षा कमी येणार ना? हा
नाही नाही,
जास्त.
जास्त येणार.
हा
कारण
हा
हा या स्ट्रेसची व्हॅल्यू बरोबर सिग्मा ई डिवाइड बाय फॅक्टर ऑफ सेफ्टी असणार आहे,
येस सर.
आणि सिग्मा ई पेक्षा ह्या स्ट्रेसची व्हॅल्यू कमी आहे. ओके, म्हणजे
येस.
फॅक्टर ऑफ सेफ्टी इक्वेशन ते इक्वेशन काय येणार आहे की ह्या इफ आय से दी स्ट्रेस एज अ sigma This value, this I call as a sigma Abhijit A. Okay. Abhijit stress value. Now, how we can calculate the factor of safety? We can write equation that is sigma A is sigma A this sigma A is equal to sigma E divided by factor of safety. Sigma E divided by factor of safety. So what value of factor of safety we can get? This factor of safety is equal to, we have to take this sigma E divided by sigma A. Sigma E divided by sigma A. बरोबर है?
Yes, sir.
Now what value of sigma factor of safety we are going to get? Definitely it will be higher than 1.
Yes, sir.
Because sigma E has a higher value than the sigma A. Right?
Yes.
Likewise,
Yes.
for this point also we are going to get the factor of safety which will be more than the factor of safety which we have calculated right now. Right?
Yes.
Okay. That
Yes.
means we are going to make more step design. Got it?
Yes, sir. Yes, sir. What?
Can we go further?
Yes, sir. Yes. Thank you, sir.
So this is what just now I have explained. I have written here the description for the same as the Soderbergh diagram. Only important is that now we will consider the similar triangles. Okay, the similar triangles in the diagram here in this diagram. The similar triangle as COD and PQD. Okay, these are the two similar triangles. Once again, I will repeat the similar triangles as we have already mentioned in Goodman diagram that COD and PQD. In this case, if we are going to take the ratio of PQ, that is P to Q, okay, we will take C to O or CO, okay, from the triangle, bigger triangle, is equal to QD, that is QD value, divided by OD, that is for the bigger triangle, OD. Now for this QD, we can write as a OD minus OQ. Okay, so this equation will become 1 minus OQ, which is this value OQ, divided by OD, that is O to D, right? Because this OD will get cancelled here, we can write 1 when we are going to divide by this denominator for these two variables. So it will become 1 minus OQ divided by OD. Okay. So when we are going to put values for these lines which we have considered, a PQ line, P to Q line is indicating sigma V, that is variable stress value for point P. Okay. So variable stress value we have put here, divided by CO line. to O. It has a value equal to endurance limit divided by factor of safety. So here we have written endurance limit divided by factor of safety is equal to this 1 minus OQ, is O to Q value. It is equal to the mean stress value for the point P. Okay, so the mean stress which we can apply or which will get generated when we are selecting point P, that will be sigma m. So here we can write sigma m divided by OD, that is O to D distance, which is equal to this yield stress divided by factor of safety for the same material. Okay, so here we have written as a yield stress divided by factor of safety. Now further, if you are going to solve this equation, we will solve that equation. But here I want to mention one more thing, that the factor of safety which I have considered in case of this endurance limit and in case of this mean stress. So mean stress is not changing its value for the given application. Okay, if you are going to select different cycle of load, it will become different. But for the same cycle, for the same load or the case which we are going to study, that mean stress value will remain constant, right? But the factor of safety which I am going to consider for this mean stress, that is normal stress, tensile or compressive, that factor of safety and factor of safety which I am going to select for the variable stress is, if it is same, then we can take it common. And in some applications, if the stress is different, then we have to use the value of that factor of safety for that particular application. Okay, I will repeat it once again so that you can मी काय म्हटलं ते समजलं का?
रिपीट करा सर एकदा.
येस, ज्यावेळेला आपण फॅक्टर ऑफ सेफ्टी कन्सिडर केलाय मीन स्ट्रेससाठी काय फॅक्टर ऑफ सेफ्टी आपण कन्सिडर केलाय, दॅट इज एफएस. ओके, आणि मीन स्ट्रेस ही व्हॅल्यू आहे जी आपल्या केसमध्ये चेंज होत नाही. ओके, व्हेरिएबल स्ट्रेस सारखी नाही ती. जरी आपण सायक्लिक लोड अप्लाय केलेला असला तर त्याची एक व्हॅल्यू, त्याची कॉन्स्टंट लाईन आहे, मागच्या क्लासमध्ये आपण बघितलं. ओके, पाहिजे तर मागच्या मीन स्ट्रेसचा रेफरन्स. येस, ठीक आहे. समजा असा सायक्लिक लोड आपण अप्लाय करतोय आणि त्यासाठी आपण सोडरबर्ग डायग्राम बघतोय. आता ज्यावेळेला आपण हा मीन स्ट्रेस जो अप्लाय करतोय किंवा सिग्मा एम, हा मीन स्ट्रेस जो आहे तो मीन स्ट्रेस साठी जो फॅक्टर ऑफ सेफ्टी आहे. ओके, कारण हा जो स्ट्रेस आपण घेतलाय तो मीन स्ट्रेसची व्हॅल्यू घेतली. ओके, जो टेन्साईल किंवा कॉम्प्रेसिव्ह असं अज्युम करतोय आपण. आता ह्या केसमध्ये तो फक्त टेन्साईल आहे. काही ठिकाणी विल गेट दॅट व्हॅल्यू एज कॉम्प्रेसिव्ह ऑल्सो. तर त्यासाठी घेतलेला फॅक्टर ऑफ सेफ्टी म्हणून आपण या इक्वेशन मध्ये काय केलं की एस वाय डिवाइड बाय फॅक्टर ऑफ सेफ्टी घेतला. आणि हा जो व्हेरिएबल स्ट्रेस आहे वाय ऍक्सिस वरचा, तो व्हेरिएबल स्ट्रेस साठी आपण एस सिग्मा ई डिवाइड बाय फॅक्टर ऑफ सेफ्टी घेतला. आता हाईटला जर व्हेरिएबल स्ट्रेस साठी मी फॅक्टर ऑफ सेफ्टी ठेवणार आहे 3 आणि मीन स्ट्रेस साठी जर फॅक्टर ऑफ सेफ्टी ठेवणार आहे 2, तर ह्या दोन व्हॅल्यू वेगवेगळ्या आल्या. त्यावेळेला आय कॅनॉट टेक इट एज अ कॉमन. समजलं? 2 आणि 3 कॉमन नसणार आहे ना त्याच्यात. हॅलो,
येस सर.
ओके, ठीक आहे. फक्त गणितात म्हणजे ज्यावेळेला आपल्याला सोडवायचे प्रॉब्लेम, त्या प्रॉब्लेम मध्ये यू कीप इन माइंड दॅट these two values as it is same, त्या प्रॉब्लेम स्टेटमेंटमध्ये मेन्शन केलं की फॅक्टर ऑफ सेफ्टी फॉर द व्हेरिएबल स्ट्रेस अँड फॅक्टर ऑफ सेफ्टी फॉर द मीन स्ट्रेस इज सेम, then we can write it here as a means that is common, that is same. If in statement it has mentioned that factor of safety which is for the variable stress is 3 and factor of safety for the mean stress is 2, then that values we have to put here for the factor of safety. Now here we are going to assume that the factor of safety for variable stress and mean stress is same. That's why we can take this factor of safety common. Sigma E, that again we can take common, and sigma v, we will solve this equation for sigma v. So we are going to take to the other side and we are going to get value that is equal to sigma e divided by factor of safety into bracket 1 minus this sigma e divided by factor of safety we are going to take to this side, and it will be my 1 minus sigma m divided by sigma y, that is the yield stress, divided by factor of safety. Okay, now this factor of safety and this factor of safety we can again cancel or we can take that common. So just we want to have this equation in sigma e, that's why we have divided by means of this factor of safety inside the bracket, where factor of safety get cancelled in this case, and we will get equation as 1 divided by factor of safety minus sigma m divided by sigma y. And if you want to calculate the factor of safety only, then we can take this to the other side of equation and this sigma v value to the other side of equation. And final equation which we are going to get is the equation which will give us idea about factor of safety, and that is equal to, as we have got in case of Goodman's diagram also. Okay, that 1 upon factor of safety is equal to sigma m divided by sigma y plus sigma v divided by sigma e. Out of this, sigma m and sigma v values are depend upon the point which we are selecting, whereas sigma y, that is yield stress, and sigma e, that is the endurance stress, are the property of that material. Okay. Now, do you have any question related to this slide? You are free to ask. Hello?
No doubt, sir.
No doubt. Okay, you don't have any doubt. Anybody else?
No doubt. No doubts.
Okay. Anybody else? Deshmukh, Pratik Deshmukh. Deshmukh. Can you hear me? Hello?
Yes, sir.
Okay. Do you have any doubt? Hello? Hello? If not, we'll move further. Okay. Further, what we are going to consider is that the various factors, because when we are going to consider the sigma E value, that is the endurance stress value, that endurance stress value as it is, if we are going to take from the Morse experiment, then the actual sigma E value, because we have seen an expression for actual endurance limit and the endurance limit, that is theoretical endurance limit, which we are getting from the experimentation. So in that case, only here is Kf, where the Kf is what? Stress concentration factor has considered, and we have rewritten that equation for the factor of safety as we have written for the Goodman's diagram. Now we can use this Soderberg's equation or Goodman's equation for the solving of problems related to the fluctuating type of stress. Any question? Hello? If not, here on this slide, I have shown the comparison between Soderberg and Goodman's diagram. Now, in case of Soderberg and Goodman diagram, what we have done? That here, this region, can you see this region? Where it has written as a unsafe, this region, which is related to the yield stress value and ultimate stress value. This unsafe region, if the point is lying in this region, that has mentioned as an unsafe region by means of the Soderberg. Whereas for the Goodman, that region is safe region. Okay, so that is what the difference between this Soderberg line and Goodman line, and hence this Soderberg line is what we can say more safe as compared to the Goodman line. Any question? Hello? Hello?
No, sir.
Okay. If not, I'm going to take presenting. Just a minute.